Demonstration problem. Find the tension in the cable and the compression in the light beam supporting the sign shown below in the picture. The givens. We have that the magnitude of the weight of the sign, or more formally with this notation, is 750 newtons. The mark over the zero means that that zero is a significant figure. The angle theta between the horizontal beam and the rope supporting the beam is 40 degrees. The unknown. What is the magnitude of the tension force in the wire supporting the beam? And what is the magnitude of the boom force? By analyzing the lines of actions of the three forces, we see that they are concurrent at a single point, this point P. This is the line of action of the tension force. This is the line of action of the boom force. This is the line of action of the weight force. They all intersect at point P. That will become the particle at which all forces are concurrent, and that will be the origin of the coordinate system for our force diagram. Note that this is a light beam. That means that this beam has no weight. If it did, we would have a weight force vector at the center of gravity of this beam. This weight force vector would not be concurrent at point P as this system of three vectors currently is. We would have to use a different technique than the present technique. That will involve torque, and that will come in a later section. Before proceeding with our solution, we construct our force diagram with the origin at the point of concurrency, or point P. We then put the tails of all the force vectors at the origin at point P. The boom force, F sub B, is this vector out the positive x-axis. The tension vector is depicted here in the second quadrant, and the weight vector is out the negative y-axis. We see that the unknown magnitude of the tension vector is the hypotenuse of the right triangle formed by the x and y components of the tension vector. The equations. Since this is a concurrent force system that is at rest, we have equilibrium in two dimensions. Therefore, the equations are that the total force along the x-axis, or F net of x, is 0. F net of x consists of the x component of the tension vector plus the x component of the weight vector plus the x component of the boom force vector. Likewise, the total force, or F net of y, along the y-axis is 0, and it consists of the y component of the tension vector plus the y component of the weight vector plus the y component of the boom force vector. Substitute. For F net of x, we have that the x component of the tension vector, it is negative, so we write a minus sign, magnitude of the tension vector, which is the hypotenuse of this right triangle, times the cosine of theta, which is 40 degrees, plus the x component of the weight vector. The weight vector has no x component at all since it is directed out the negative y-axis, plus the x component of the boom force vector. The boom force vector is along the positive x-axis, and therefore it is positive the magnitude of the boom force vector. What we now have is one equation in two unknowns. Therefore, we write the equation for the total force along the y-axis. Substituting into F net of y, for the y component of the tension vector, we see that that is positive. And so it is the hypotenuse, or magnitude, of the tension vector times the sine of theta, which is 40 degrees, then plus Fw sub y. The weight force vector is directed out the negative y-axis, and therefore it is negative. It is negative the magnitude of the weight force vector, which is 750 newtons. And then plus y component of the boom force vector. The boom force vector has 0 y component, so plus 0, and that is 0. We see that this equation is one equation and one unknown, which is the magnitude of the tension vector. We can solve it explicitly for the tension vector and then substitute what we get back into this equation and then solve for the magnitude of the boom force vector. Solving this equation for the magnitude of the tension vector, we get that it is 750 newtons divided by the sine of 40 degrees, which is 1167 newtons to 4 significant figures. We carry 4 significant figures since this is a 3 significant figure problem. We now substitute this value of 1167 newtons for the magnitude of the tension vector into this equation. We have now solved the problem. The magnitude of the tension vector to 3 significant figures is 1170 newtons, and the magnitude of the boom force vector is 894 newtons.